All right, so I'll be the next one, right? So they changed the PowerPoint. So again, I'm James Chen from the Department of Power Mechanical Engineering, and it's my pleasure to give a talk today, a short talk today, to share about my recent development about robotic hands. So following up with the Professor Ling's talk, so I think the arrangement for today's seminar is very excellent. So you talk about the chemistry, this kind of very smart sensor. Then we talk about the application, and so since I'm in mechanical engineering, so basically, pretty much from engineering perspective to talk about how we develop by using a mechanical method for sensing. Okay, so you can see about in our research center here, Professor Ling is very detailed scientific discovery about using chemistry to have a detection kind of feeling. But mechanical engineering is a heavy duty muscle. So basically it's different level of sensing, okay? So going to talk about the manipulation and the sensing with the human-like robotic hand. Right, so first of all, I wanted to give a brief introduction about myself, and then my first job after getting my PhD from Carnegie Mellon is to work as an engineer and researcher in IBM research, and specifically doing the magnetic disk drive development. I'm sure that most of you probably have no idea because most of you are very young. But if you are over like 45, probably you used a hard disk drive before. But right now, there are lots of this kind of data center in the world, right? So basically, put a lot of data in the magnetic because it's cheap. It's cheaper than the solid state. So anyway, so my point is that since I'm not directly into academia, so I'm kind of think of myself as an engineer. Even though I travel around different countries and teaching in New Zealand and Taiwan and USA, but pretty much I'm still consider myself an engineer. So that leads to today's style is that I want to kind of give a talk in terms of engineers. So define the problem first. Then, because our center is about internal sense, right? Sense what? So sense of what, right? So you are talking about, you have to define the need first. Then we talk about how do we put the high technologies and integrate all the discipline research together to kind of generate value. So I'll give you an example here is I kind of use robotic technology to kind of enhance or help the patient to cover from the stroke. So the first question is, why we talk about the robot using this kind of rehabilitation or manipulation with the human beings. So you can see that on the left-hand side here, so the world is aging. It's not like I know that most of you are very young, but if you go to Taipei, more than 50% of people are very old. Okay, so basically older than me. So that means that in 2025, which is next year, and 15% of people are over 60 years old, and then 25. This one in 2050, you have 22%, not just in Taiwan, but worldwide. But Taiwan actually is very, very aged country, okay? So you can see that, in 2025, next year, we are super aged. So congratulations, most of you are very young. So you are the precious of Taiwan. But but on the other hand, put a lot of pressure to young people because you have to work very hard to produce the value, to produce the money, to cover the health need for aged persons. Okay, so that's another drawback about the aging population. Right, so the following talk will be kind of organized in these 4 categories. The first thing is identify needs. So we talk about how we identify needs and the technology gap. The second is based on the needs, we kind of come out with a design for biomechanical requirement in terms of mechanical, okay? And then we talk about the engineering design, verification, and then also about the development phases. Most of the professors and students in university pretty much are not familiar with how product is developed in real industry. So it's more like from the scientific discovery and push forward to create a market. But actually, so that'll be too much effort. So on the other hand, you can define the needs first and then come up with a proper design, and then with the EVT, engineering verification test, and design verification test, and then at the end, customer verification test. Then you can have a product. So without the proper definition of needs, probably my experience is that at the end will be invade just publications, but not really generate income. I know that in Taiwan, professors are very, the income is not as high as in USA. So that's the reason I try to use this one to increase my income. Okay, right. So the needs. Why talk about this kind of topic, and the opportunity? Again, you can see your left hand side here. For each one of you, you will be right now you are young, but 10, 20 years later you will become very old. I'm sure that Professor Ding probably know the slogan here in Chinese, So just like when you are young, you are dating with your loved ones, but you just we have a romantic event. But when you become old, that's just a single event. And when I was young, I would show off that, okay, I can run 5 kilometers per day and push up 100 times, right? But right now it's only in my brain and I can only talk. I cannot do that anymore. So, but that is the fundamental needs. It's a fundamental needs for everyone. I'm still young. I still want to do the things I used to do. So that's the needs that really generate and drive the market. So you have to clearly define the needs. And in this kind here, sorry for the Chinese here. So in Taiwan, is that because the age population, so the healthcare demands can increase. But the young people like you don't get married, you don't produce babies, right? So basically there's no enough human power to take care of the aged person, right? So that is the problem, but also that's because the demand and supply is not balanced. So that will create lots of issue here. But if there's an issue, there's a possibility and the opportunity there. So in terms of healthcare with the robot, I think that's a good because the needs there is increasing. And then and how do we combine with the good technology, especially in Taiwan here, in Silicon Valley here, Silicon Valley of Taiwan in Hsinchu here, to get together to help our society to kind of have a better future. So why? What is the rehabilitation? And then rehabilitation in most Asian countries, kind of think about that rehabilitation is like massage. But actually, it's not. It's a medicine. Okay, it's a medical treatment. And if you go to overseas in New Zealand or UK or USA, the rehabilitation center is not like here, as shown in our screen here, like in Taiwan. In Taiwan, everything is packed because we got too many old people, too many people to require the rehabilitation. But from the other hand, suppose our rehabilitation treatment can be like a very high-end, very relaxed, this kind of environment, enjoy, and then you still do the rehabilitation. That will create another business, and you will create a different market as well. So can we, and given that we do not have enough people to do this kind of thing, so robotics actually is the key thing to do that. And right hand side is a rehabilitation. Is it for old people? Actually, no. This is my pictures 13 years ago, even though I look the same, but my physical body is become old, okay? So I have to go to the hospital to do the rehabilitation, push up pull my neck because I use the phone, cell phone too much, okay, computer too much. So it's not just for old people. So we step back here to think about, okay, now the needs there, the age is not just target for more than 60 years old, so all the age, pretty much you will create a lot of market, right? So if we can think about this, this is a good research area. The needs there is not unsolved. If this is solved, so what? So if you do a lot of this kind of minor improvement of that will not generate money, okay? So why do we have robotic hands for medical manipulation, and how's the market? Now, so in the present treatment, rehabilitation treatment, pretty much as you can see on the screen here, is the kind of treated by one. So basically, a patient had to be accompanied by a medical professional. Okay, so from mechanical engineering perspective, this is a labor-intensive industry. Just like in Taiwan 50 years ago, we manufacture by hands. Okay, we also assembly by hand. But now in Taiwan, everything is automatic. Everything is like AI with this kind of smart manufacturing. So that is right now the industry in medical industry is labor intensive. Okay, not enough people, right? So you don't want to be a doctor because there are lots of issues about the legal issue. How about we use a robot to do that? So that is the kind of another unmet needs we have to fulfill with the robotics. And yeah, great. So we got everything you can market and your needs in the age sectors all met the requirement. How about the foreseen market? Is that just saturated or is it growing? If it is saturated, so what? It's saturated. Then if you invest a lot of research to integrate all this technology together, it's not going to generate new things. Okay, it's not going to outbid your competitors. So we kind of see from here, you can see that right now we are 2024, right? So it was projected that in 2030, it's going to double. The market is double, okay? And it's supported by the aging population worldwide. And given that a couple of years ago, we have this kind of COVID-19, so nobody want to be touched by people, right? So could be touched by Professor Ling's sensor because no human, right? so that is another means that we can do that. So before you do your research, I actually do a research, I kind of investigated this kind of requirement of multi-sectors, the needs and supply. And before doing that, you have to kind of realize what is your standpoint. Your standpoint is a starting point, your universal research point, or there's a lot of smart people out there, okay? There's lots of people working on the same thing out there. You need to look at that. So I kind of review all this kind of adjacent market. So for example, your lower limb, the legs, you can put a robot on that, right? So got lots of competition. You can see that. You got this kind of Hokoma. You have this kind of Taiwan. We have still the same thing. You have high wind. Each tree you have to do that. So in the upper limb, you have this kind of thing. But funny thing is that the other thing is you can see those companies. Most of them are not Taiwanese companies, but surprisingly, each price here is very, very high. Okay. Probably you will see that it's more like 5 times than Taiwanese product. But when you open up the machine, 80% of the components are made in Taiwan. That's kind of interesting. So you can see that we are good in Taiwan. Our technology is good. However, when we define the market sectors, it's not smart enough, right? So if you are Taiwanese, you can see that how do we leverage our things and then how do we combine all the technology and with this kind of market-driven design things. So I will share with you how I did it. It's an example from university research to market. Right, so the current status about the rehabilitation of the hands, for example, if you have an elder in your family, probably will subject to stroke, right? When you're subject to stroke, about 30% of people have to go to hospital. The 60 to 30% probably will recover. Okay, and then the X-ray is required to be treated within 6 weeks. After 6 weeks, you go to hospital, nothing there. But now think about that. In Taiwan right now is we do not have enough medical professionals to one by one treat your rehab your hands, right? So you have to wait, right? Not to talk about in USA, you go to check with doctors, you have to wait for 2 weeks at least. I live in USA for a long time, at least 2 weeks. Okay, so pretty much you will miss this golden age, golden period. So we require rehabilitation. And why the hand rehabilitation has not been fully investigated or have a product? Because it's very complicated. Sensing is a problem. Okay, and then the mechanical is very complicated. Lots of components, so it's not easy to design and maintain. And so this is a kind of limitation. You can see that all this kind of research published in top journals, and so basically, this there we got this kind of robotic hands, okay, or what we call the exoskeletons, but they are pretty much starting from engineering perspective, but not from the needs perspective. So when they design things, for example, here, it's too bulky. much of things. It's not satisfying the medical requirement, so the doctor is not going to use. So you say, oh yeah, great, you have great research, so I don't want to use. So basically, from a research perspective, you cannot put your research really into the market. So, okay, and also very expensive, So here you can see that the most existing devices is about $50K to $60K US dollar. Ooh. So your professor project, probably each year's project in Taiwan is like about this, right? $50K US dollar from the National Science Technology Council, right? So yeah, actually, it's quite expensive. But from a mechanical perspective, yeah, how come it's so expensive? The cost is not expensive. Okay, so here's the existing product. Left-hand side is the Hong Kong Hand of Hope. Was produced by a professor from Hong Kong Polytech, but was the kind of technology transfer to Chinese companies. And then here's another one in China, which kind of copied the design from Hong Kong Tech. Okay, so but again, they started from what? From engineering design. Okay, so yeah, you have a EMG, so you can move your fingers. It's not going to solve the problem. So in rehabilitation, is going to solve for example, everyone has hands, right? So when you be subject to the stroke, it's very tight. So the problem is the issue is to loosen up the joint, right? So loosen up the joint, and you have muscle there, you got nervous system there. So it's not just I move, so your exoskeleton move. It's not like that. So really you have to think about what is the medical requirement for that. And the Gorilla from Italy, and then this device is very expensive. I personally look at the device, and then it's about 100,000 US dollar, one device. 100, and by all means, just a bicycle. Just like lots of wires there, right? Just like in Tsinghua University, every semester, so you have there's a junk bicycle, or a student can just tear down the bicycle and get the wire. So when I investigate these kind of devices, I go, yes, we should do that. It's not that hard. Okay, just pull in the wire, so what? Okay, and so that's the reason I kind of make sure everything. And then also before really doing that, I kind of assess my personal abilities. I'm not going to step into the research. So now I'm super duper in the world. Okay, so yeah, I did it before. So I compare with the different existing top niche product, and I found that the product, even this prototype produced by my student in Tsinghua University, actually can match, even outbid those technologies. For example, the weight and the specification, because I was an engineer, so I like to compare. Whatever engineering design, you need to have a target specification. Okay, the target specification is going to show that your advancement and among the other competitors. So, and here is another 3-finger grippers developed by my students here. Basically, actually you can see that this device, one hand, is about 50,000 US dollar. Just one hand. Okay, and this one, of course, not 50 Taiwanese dollar. Okay, it's probably the less than 5,000 Taiwanese dollar for the cost. Okay, so the thing is that my point is that when I look at this kind of review my capability in my lab, and I found out, now I can do that. It's just hands, right? I put the exoskeleton hand to human hands. The point is that I want to sense the tightness of the human hands. Here I have this kind of thing. You can put here. I can even pull the tissue papers. Of course I didn't use the Professor Ding's touch sensor, but still I can pull that. Mechanically it's easy, but can I use the mechanical method to have a feeling? Because that's the point that I'm going to show you. So before doing that, when I design my exoskeleton hands, is not just from a mechanical mechanism and design something. I have to consider all this kind of geometries from the human hands. So we did a lot of scanning, that kind of thing for that. So, and then also you can see that each one, the thumb is different from all the rest of the fingers. Okay, so the design for thumb and the fingers is different. And also when you put the mechanical, which is comparatively is more rigid than the human soft fingers, right? So basically when you bend your fingers, the rotating center is going to move. The previous reported research, they have a common problem is that when they move the exoskeleton, it's going to kind of have a relative motion between the mechanics and the surface of the human skin. So basically, it's not comfortable to do that. I've personally experienced that it's not comfortable. So we have this kind of pattern idea, have this kind of joint, virtual joint. And as I said before, it's not about the fortune teller. I scan all the Tsinghua's students and the staff's fingers, and then combined with the Chang University Hospital's database. So from that, and we can have a manufacture of the proper distribution of the size for each finger. So a couple of years ago, people talk about 3D printing. Actually, for mass production, 3D printing is just for prototyping. So we have this kind of other mechanical, like injection molding, that kind of thing for that. So we have this other thing. So that means right now, if you scan your hands, which is healthy hands, and then I will be able to pick up the proper size for each fingers. Okay, and then the manufacturing line will be combined together for that. So kind of like the same concept as what we did before when 30 years ago in Taiwan, we combined produce the shoes and those kind of different size. Right. So what? So you have the size, right? So and now, so I asked the doctor, so think about that. A patient subject to the stroke, what is the first thing he or she wants to do? Suppose your hand cannot open. So what is the first thing you want to do? Traditionally, when people talk about this kind of mechanical things, it's like, yeah, your mechanics is very easy. You can design everything. But actually, no. So you have to target the most required function. Okay? So I asked my friend from Chang Hospital, which is the head of the department of the rehabilitation. And then the first thing how to do, just open up and grasp something. Okay, open up and grasp something. So can I borrow your hand? So everyone has hands, right? So when you wake up, when you use your hand in the morning, is the first thing is like this? No, this you have to you tighten up something so you can have this kind of shape, right? Very relaxed. You open up, close up. It's very relaxed. Okay, so you can see when you close up your fingers, open up your fingers. So basically, you can see that the first thing you have to rotate is this joint here. Okay, MCP joint. Okay, the first MCP joint. And then when we move something, somehow the second joint, third joint, they will come together. So that's the reason, interdisciplinary research is kind of interesting. When I first kind of touched with this kind of human finger, this kind of mechanics, it's about mechanical linkage. It's a coupling, okay? It's a coupling. So the medical requirement is that you move the MCP finger joint followed by PIP and DIP, okay? And so that is the motion, the three joint needs to be decoupled. This one decoupled, and then so this is the kind of demonstration about the measure joint angle, which is different joint angles, okay? Then the motor, because I use the cable to pull everything. So I do not use motors for each fingers. I use only one finger motors. And the motor is not on the hand, it's far away. And transmitted the rotation through the cable. That's what I designed. You see that, wow, MCP joint, yeah, move and stop. It's not going to rotate. And here, so DIP, PIP, rotate, and move. So when I design this one and then check with doctor and then human motion, and they are exactly the same. And so what? You say, so what? Yeah, you mechanically can do that, right? But interesting is because of decoupling. So, and I pull the motion, the exoskeleton by cable. right? So by cable, so you can see that here's by cables, and I know most of you will probably think, okay, the Professor Chang is kind of interesting. It's a professor, but when I give this talk, it's just like a salesman. So I have to put some equation there. So just like Professor Ling, I put this kind of equation. Yeah, we did a lot of engineering derivation, equation, double check, that kind of thing, with the assumptions. So if you're interested in check with this paper, highly cited. So basically, I use one motors and a cable, and there's of course like a lot of force transmission. I have to do the calculation. So the previous page we talked about is decoupling, and I use tension cables, okay, to drive that. You said, so what? And funny thing is that I figure out I can use the cable to sense the force. Everybody graduated from high school here, right? Of course, right? So how do we sense the tension force in a cable? The very easy thing, so here, if we can measure the force here, and we know the angle here, pretty much you know the tension force here, right? Everybody knows. And I was surprised this simple high school concept can get a US patent. That is the kind of interesting thing. So what I'm trying to say is that it's not going to really have a value. It's not just put lots of technology, which is intensive research technology. But firstly, if you can identify the needs and then kind of match the required technology to fit that, and you pretty much can generate money or generate the output, not only the money. Okay, so I put this one, I combine with this kind of cable-driven mechanism, and so the idea is, okay, now just exoskeleton with a human finger, right? So I pull the rotating motor, which is I pull the cable, and the vertical axis is the measured tension force from the cable. Okay, so when you rotate, so basically exoskeleton is moving, and so you can see that from 0 degree to here, so you basically, the force is going to increase, right? And another stage, another force is going to increase. So you can see here, this one is a dashed line is a simulation from my mechanical models, okay? And then for MCP and DIP, okay? And the blue line is experiment data, it's the average one. You can see here is a little bit light blue area. It's a measurement of 100 times. Mechanical engineering have to what? Make sure the repeatability. Okay, it's not just one-time event. Bang, we measure 100 times, and you can see the scale here is here's 5 Newton, right? What do you mean 5 Newtons? So if you have 1 kilogram, subject to 9.8 is roughly 10 newtons. So 5 newtons is what? It's about 0.5 kilogram. And this range here probably less than 100 gram. Okay, and the question is that good enough? And I asked the doctor, in present medical testing, it's not going to sense the deviation of 100 microgram. It's not. So I make sure my resolution is good enough to cover that. And then simulation, and this one is good enough. And this is for the index fingers, and this is for the so this is for the index finger flexion, like this extension. Okay, flexion extension, and also measure all the things, the middle fingers, little fingers, thumb, for flexion extension 100 times. Make sure the mechanical is okay. My model is okay. Probably you'll ask a question, so what? Yeah, you are great. You are the great mechanical engineer. What about the sensing? Yeah, you sense the force. Take a look right here. So here is the force, right? Is the force. And here's the angle. Angle means what? Just like displacement. So everybody probably know that you want to know about the slope, F equal kx. In high school, you have a spring, right? You have pulling force, right? You have spring constant K. So pretty much you can extraction of the spring is the displacement. So you know the displacement, and you know the force, and you pretty much know the stiffness, how tighten your finger is. It's not about measure the tiny motion. It's more about the force. Force control and force sensing actually is a key for rehabilitation. Okay, so here's only for the exoskeleton part. What happened when I put the patient's finger on with the exoskeleton? So here's the clinical validation. So I've finished the engineering validation, and here's the clinical validation. We call the spasticity with tension. So left-hand side, there's a healthy subject. Right-hand side here is a stroke patient, heavy stroke patient. And probably here's the middle. So you can see that when I circle by those things, the healthy one, when you compare this one and this one, what's the difference here? Here is the healthy one. This one is a middle stroke, okay? Heavy stroke. So the deviation, the increase or change from the healthy one, that's just an indication about the tightness of that finger. Given that your MCP joint and the rest of the joints are decoupled, so that means this is MCP. Just the bigger. So it's basically very tight. Okay. So now in Taiwan we have this technology. We can real time sense your stiffness, how tighten your finger is, all the fingers, and only one line, one cable, and one motor, and that sensitivity is about 100 grams, and which much can be used. So we have this kind of using mechanical method to kind of detect the so-called spasticity, or mechanical is about the stiffness or torsion stiffness of the joint. And think about that. If you have a Rosen screw, right? Rosen screw, how do you tighten up, or how do you loosen up? Pretty much you have a screwdriver, just to loosen up. You exercise a couple times, right? So the same thing in medical requirement. So basically, before the use in hospital, I kind of spin off the companies in Tsinghua University for almost 10 years ago, right? So basically done by my students, and then so I advise my students. So we have this one here and this one here. You can see that because I define the needs clearly, and the endpoint is to use in the hospital. So I need to have what? I need to have a FDA requirement, their approval. So we obtained the Taiwan FDA, and also in 2019 we get the US FDA. Everything from Tsinghua's lab. Okay, so and usually in biomedical devices, you have to spend more than 10 years. And I just started like 2006, so only 3 years, I get the US FDA approval. So which is great. Okay, so and so because I usually work in Silicon Valley, right? So I kind of I know students probably do not believe professors, right? So you talk about spin-off companies. I really kind of demonstrate how to use the university R&D to spin-off companies. So starting from R&D, university R&D, then we have patents, this kind of regulation, passing the regulation of the GMP, ISO, that kind of thing. So now the company is in Zhubei County, and then and also we have applied this one. Actually, I was asked by previous President Chang to demonstrate this kind of thing, but because I'm a professor, I think student did all the work, so let student to do that. So my student, so all the professors there, the President Chang stay in front of my student 10 minutes. So the rest of professors, yeah, good job, yeah. I think that just demonstrate how Tsinghua's education can kind of excel the other universities, and also the MOST or now the Taiwan National Science Foundation witnessed to this kind of CES show a couple of years ago. Right. So what I want to say is that even though what you see here, the technology is not that high, you will say, mechanical is not high. But if you care for it, look at the needs, define the needs first, and define the unmet requirement clearly, everything is possible. Okay, the sensing, you can use a mechanical, like a spring. You don't have to use a very, very, very fancy stuff. Basically, the cost is very low, just a spring, just use the cable. Okay, so and I also asked my student to participate actually in the Medica 3 times. There's a saying that you participate in Medica 3 times, you still survive. Your company is going to okay. So now it's really okay. So it's getting a lot of money. So and some of you are students, right? I kind of encourage you to kind of work as a PhD student, master student, only 2 years, not enough time. PhD, 3 years, 4 years, you can do a lot of a real thing, and then our Tsinghua professor can pretty much, work with you directly for that. And here's my students, demonstrate this one in America, you do that, right. So, well, I want to make another point, even though it's about the centers, kind of research centers, but I would say that our output, we also need to consider the beauty, about the design, not just a very Taiwanese style, very Asian style. No, there's another respect to our design, our technology. So you see this kind here, nobody believes this is from Taiwan, probably it's from Germany, from USA. No, it's 100% design made in Taiwan and by Tsinghua students. All right, here's some demonstration. We got this kind of technology and attract lots of media attentions. And sorry for the Chinese description, but basically is that what I'm saying is that in the past, the patient subject to stroke, you hide your impaired or damaged hand in a box, and the box is covered by the mirror. We call it mirror therapy, and the patient use a healthy hand to say, okay, I move this finger, and then imagine your impaired hands can move. That's kind of strange to me. For mechanical guys, why doing that? You look at this one and this one. So I designed this kind of devices because this is a previous method. So now the patient can wear the exoskeleton with the sensing and move their healthy hand or move by the doctors. So to see the impaired hand can move. So that's the idea, and which is new. And actually the first one in the world, and all designed and by Tsinghua. Right, so here, I think there's a video here. You can see that you can play that. You can play the video. 你可以按一下. Right, so there's another one is what we call mirror hand. It kind of reflects the situation in Taiwan. Here you can see here is a computer scientist, so he is using her hand all the time. Her father actually is age, just like most Taiwanese families. The family, and then the father is age, is old, right? How can we take care of the daughters, right? So you can see here is her left hand was not functioning. So now is wear this kind of device, and actually is recovering right now. Actually, she has already recovered. So you can see the description here. Here's this hand here with a sensor, basically can detect the motion of the healthy hands. And then the exoskeleton will duplicate the healthy hands motion to do that. So the doctor do not have to go there. Let's move the index finger, middle finger. You don't have to do that. You program that. Or you can record the doctor's motion, put in the computers. Actually, the computer just that device. You don't have to use another computer. Just that device is a computer. It's a wearable. You can think about it. It's a wearable computer with a smart detection and smart algorithm to detect the stiffness of that. So you can see that this is the case. So immediately after the announcement of this product, those first-tier international companies contact me right away to kind of combine with my hands. Of course, I'll be very happy to combine Dr. Lin's touch sensors for this kind of more detailed sensing. All right. Yeah. So now we'll reduce the rehabilitation medical professionals loading a lot. So one person probably can take 10 patients at the same time, and then also have the data, but not just let's do exercise and then no data. All right. So now, I think the last slide is about I can move forward and work with most of the professors in this center under this kind of we call it Tsinghua Gentleman dual arm AI robot. And so I know the CEO Huang from NVIDIA was talking about the human-like things. Human-like robot. In fact, in Tsinghua University we already did it, and we have AI chip inside. So here's kind of like a commercial, not commercial, just the video kind of summarizing what we did before. And if I have time, you can contact me, and then can go to my lab. I'll have this kind of dual arm human-like robot. Now the robot, actually the development of the robot actually is not just mechanical. I have electrical engineering, which is from Professor Wu Chengwen, which now is a Director General of the Taiwan's NSF, and then have a professors from the computer science also. So we have this integrate all the technology together, but because we know there's a need there. So in the future, the human-like robot will have a self-sensing. So basically, for example, I can see something, I can recognize something, so my mechanical can go there directly without doing any computation. I mean, not doing any teaching. So right now, all the robot have to program first. So now all robots here have this kind of automation or very with the smartness. And this is the Professor Wu, and then we have this chip inside the brain of the robot. And the hands not touch the tension sensor in that, so we can get this kind of thing together, recognize the object, pull the waters, so when we change the weight, we know how to grasp it closely, just like human beings. And the goal is that in the future, actually right now, the robot has been trained to become like a worker, technician, to help the Taiwan airspace industry to cut something very hard. And so basically learn the skill from the human, and it's going to have because I have the force sensing, so you can know the force, just like you're cutting the apples. So right now the robot can do that. So all of which is about the integration of all the technologies, and then about those my colleague in Tsinghua University, and we have an excellent colleague in Tsinghua University. If you want to work collaborate with Tsinghua University, please you look at the video. Just call the contact person in Tsinghua, and we will be able to work with you directly. Right, so I say that I was moved by Taiwan when I was young. Okay, when I was working overseas, every time I stop by Taiwan, there's a Taiwan will touch your heart. I went Taiwanese, so I decided to come back to Taiwan, not to show all my things in IBM and Silicon Valley, because I want to contribute to my country. So you can see that our Tsinghua have lots of opportunities and upper technology, and actually in depth as a world class. So welcome to come to Taiwan and just work with us. So I see that Taiwan is a cradle of the first class talent. Got lots of talents. Okay, so because I know this video is going to sense overseas and through the internet, because the center is the Internet of Things, right? So I hope that my talk today can touch your sense, So we have this kind of collaboration is a key to value generation. So do not hesitate to contact me, So usually from one area is good, but actually you combine different area will be great. So you create lots of values. All right. So thank you very much for your listening, and I'll kind of finish my talk today. Thank you. Okay. Any questions? No questions. Right. Yes.
One question.
Yeah.
About the hand of some of the fingers are really used. It's like the 3 fingers and the little fingers. And why not to make only 3 fingers of the robot hand, which can reduce the complexities and the cost significantly? Okay,
so it's a great question. Actually, you're right. The design of a human fingers, actually this pinky finger and this one here, pretty much is used to hold something. Okay, hold something. And most of the time, we use the thumb, index finger, and middle finger to do something. Hold something and do something is different, right? For example, you rotate something, you do probably these 3. And so you can, if you go back to my, there's a comparison of the different product already designed. And actually, we already designed it. Okay, but of course, there's 3 fingers of that. But for the rehabilitation, some patient basically some these middle fingers actually is subject to stroke, because the each finger have a nerve, and the nerve is centralized in the brain. Okay, so it's about neurology combined with this kind of biomechanics. So actually, my tech here is due from mechanical to kind of stimulate the neurology. Okay, so for example, probably everyone here know that when you die, your body becomes very stiff, right? Very stiff. You die, it's not soft. No, all the body is stiff. Okay, but the healthy person actually is not stiff. Why is that? Because the neurology system have a stimulation to the muscles, and when a patient such as a stroke, basically this stimulation is reduced. And so our approach is from mechanical to stimulate the stimulation to do that. Okay, so we designed this 4 hand. That means 5 fingers to do that. Of course, you're right. For other application, 3 fingers is good enough. And this one here, you can see here, actually can change the size and change the orientation of the 3 fingers. You can have, for example, a triangle shape, irregular shape. Basically, this one can do that. And because here also have a sensor, it's an image sensor to detect the object you're going to hold. For example, this kind of pointer is a rectangular shape, right? It's stupid to use a triangular orientation to grab something. You have to do that, right? It would be easier to do that. So now in my lab, actually, I have this one ready to show. Designed by my PhD student and already technology transferred to High-Wing company already. Right? Did I answer your questions? All right, thank you. Any more questions?
So you just, Professor just says, so you wonderful talk. So you just mentioned the price, right? So how about
the price actually right now from my spin-off company. And by the way, I'm just an advisor for that. So it's not I do not own the company. Okay, my student own the company. Anyway, so the price for one hand, one system, $50,000 US. Good, right? So it's good money, right?
Yeah.
$50,000 US. And actually, it's just pretty much meet the same price about the competitors. Actually, our functionality is much better than that. And so that's the reason, because we clearly define the medical needs, but we do not reduce the price. I know most Taiwanese companies say, oh, cost down. So my value is that when it goes cost down, there's a limit on the ground, right? So when we talk about value up, right? So there's no limit in the sky. So why don't you just value up? So it's quite stupid that also manufacturing in Taiwan is cost down. But we need to clearly define the functionality, which has the value. Don't reduce. Oh, I'm very cheap. No, we are not cheap. Professors are not cheap. Our intelligence, Taiwanese intelligence, is not cheap. Okay. Right, so if there's no other questions, I think I will let you go. And thank you very much again for your attention. Thank you.